Thank you. Thank you very much. It's great to be back here, and I want to thank Jason for inviting me back. I did a keynote at the first Monitorama last year in Boston, and met a lot of interesting people, some of whom I've kept in contact with and met here again, so I have to keep doing this actually, it'd be quite good. So, the title, I have no idea what this really means. Although it's alliteration, that's been observed already. The key motivator was to be able to use the word melange for the first time in a talk, so I've managed to pull that off. As far as introductions are concerned, I think some of you are already aware of these books, whose author bears some kind of resemblance to the person giving this talk. So, I heard some rumour about no more aircraft crash slides or something, but it's too bad because I didn't go to Monitorama in Berlin. I think that came up, so I didn't get the memo. So, it turns out this is actually very useful for what I'm trying to say, so I'm going to use it. In case you don't recognise this, this is San Francisco Airport runway almost a year ago. This is Asiana flight 214, landing arse backwards. Someone's tail. The tail came off at the beginning of the runway. They actually managed to slice it off. So the point here is that the various bodies that have looked into this crash, and I guess it's still being investigated to some extent, but those in the know recognise that this is largely a problem of the pilots having become over-reliant on their instrumentation and don't know how to do things like manual correction, and perhaps even look out the window, which would be handy at times, I think. So I want to make the same point about your instrumentation. And what I'm going to talk about is how to avoid being just reliant on these endless strip charts that we've been seeing for the last day or so, or other shiny things. It's not about the pictures. It's not about the whiz-bang tools either. It's not about the fancy math, even though I'm a big fan. The data is trying to tell you something, and your job is to try and figure out what's the message in the data. And that means that you have to interpret it, which has got nothing to do with pictures, tools, or math. It's actually to do with this cognitive processor up here. And the point is you need to reach some degree of consistency about how you're interpreting that data. And also other information that's available, because there's always some context. So this talk is, in spite of the title, really about how to converge on consistency, and there's really no algorithm for that, because there's a certain amount of art in this science. So I'm going to try and show by example, including some things that I've actually worked on. I don't have the time to go into great detail about it, but if you're interested we can talk afterwards. I'm not leaving for the Bay Area until this evening. Or if you get really wound up, you can come to my classes and we can talk about it for an entire week. So, I'm going to start off by showing you what is plausibly the most important scatter plot in the history of mankind. And it starts out in the way that you're now familiar with. So I'm just warning you, goggle up science ahead here. So it starts out with the time series, which we've been seeing for the last couple of days, and these are the sort of instruments that you're used to looking at. So you're used to looking at strip charts or typically time series. So here we have two metrics, I'll just call them metric 1 and metric 2. They have their own time series. But the time series really don't tell you that much, and the brain has a really hard time trying to interpret what the time series means. If it didn't, we'd already cleaned up on the stock market. So the thing you have to do is to transform this data in a way that it is more accommodating for the cognitive processor that you're going to use. So one way you can do this is to ask the question, is there any relationship between metric 1 and metric 2? And a way to go about this, which I'm sure is familiar to a lot of you, is to just simply put the data at each corresponding time point onto a scatter plot, where the y-axis is metric 2 and the x-axis is metric 1 in this particular case. And then we can ask ourselves, based on just the visual representation of the data, is there anything interesting there? Do I see anything that might be trying to tell me something? Well, without going into too much detail, you might see a trend that's moving in a northeasterly direction, let's say. So most tools, including Excel and R and the rest of them, have a way of doing that. So if we go about doing that procedure, it's called called least squares fit, I'm sure most of you know about. There's the result that I get. And I've just put the cross coordinates in there to indicate exactly where the origin is. So you see this line happens to go through the origin. And so the relationship is that metric 2, which is the dependent variable, is related to metric 1, the independent variable, by taking the independent variable, multiplying by 423.94 to get the metric 2 value, which is relatively simple. And also we can do additional statistical analysis, some of which has been discussed in previous talks. One easy indicator is something called the coefficient of determination, or the R-squared value. This says, in this particular case, even though there's a high degree of dispersion in the data around this line, 82% of the variation in that data is actually explained by this model. That's a fancy statistical statement, but it's encouraging. It says, look, this actually might not be as bad. It's not as crude as you might have originally thought. So most people, when they get to that point, they think they're done. That's actually only the beginning, because we need to reach consistency. What do I mean by that? In this particular case, I want to ask myself, is the linear fit still a reasonable choice? Is there a better representation, something perhaps non-linear? Would that give me a higher R-squared value, or a better interpretation, or deeper insight into what I'm trying to understand in this data? What's the meaning of the slope? I know what the number is now to 2 decimal places, which is just fantastic, except I don't know what the hell it means. So maybe it doesn't mean anything if I'm doing the wrong thing. And if you convince yourself about those first 2 bullet points, are you prepared to put the family jewels on the table and use that model to extrapolate into the future? That's the real question. So this is the starting point, not the end point. Here's the scatter plot in reality. This is a scatter plot from 1929. Anybody recognize it? Okay, good. So metric 1, that's the x-axis, is the distance to the observed star that I'm looking at with my telescope. Metric 2 is the velocity that I measure when I look at that star. And this scale that's on this graph here on the x-axis is a funny thing called parsecs, which is just astronomical gobbledygook. It roughly translates into about 3.3 million light years. So each of these data took a hell of a lot of work to get. But nonetheless, that's a reasonable scatter plot. We can certainly do statistical things for that. So why was this important in 1929? Because it was Edwin Hubble who was doing the observations. This is Hubble's scatter plot in 1929. And he suspected that the velocity, the velocity with which the stars are moving away from us is proportional to the distance they are away. So the further away they are, the faster they're moving. Which in 1929 would have sounded a little bit odd. Today, we know that it really supports the Big Bang hypothesis, which is the key idea to understanding the evolution of the universe. In those days, that was a very murky proposition that came out of Einstein's equation, so nobody was completely sure. Hubble's data was the first to start to support that idea. There were some competing theories at the time, which I'm going into here. So, but this leads us now to be able to explain the slope, because the slope of that line is simply the rise over the run, which is the velocity over the distance, because that's what the 2 metrics turn out to be. If I do the little algebra there, you can see it collapses down to just being inverse time, 1 over t, which is called Hubble's constant today. So if Hubble's constant is inverse time, if I invert that again, I'll get time, in other words, invert Hubble's constant, and that time is in fact the time that the universe has been expanding, and would therefore give me the age of the universe. And that's exactly what Hubble did. So he calculated the expansion time from that data, from the slope of the scatter plot, and came up with 2 billion years. Slight problem. The age of the Earth was already known, not very accurately by the way, surprisingly. The age of the Earth has only been known in the last few decades to the degree we know it now. It's roughly 4.5 billion years, but in his day it was somewhere between 3 and 5, depending on how you did the measurements and what techniques you used. So you see, it's a little bit under, but it's not so far away, except the fact that we've got to explain how did the Earth get here before the universe. That can't happen. So it's not consistent. That's the point. Done all the math, done all the pretty pictures, but it's not consistent. Hubble knew this, obviously, he's not a dummy. What are you going to do? What would you do? Anybody got a recommendation?
Look out the window.
Sorry?
Look out the window.
Look out the window. Good idea. He looks out the telescope. What was the other one?
Fudge the data.
Not wrong. In fact, if I had longer, I could give you some interesting stories about physicists who fudged the data, including Isaac Newton and so forth. It turns out Hubble didn't quite do that, although he did try a little bit in that direction. So here's what he did. There's the data. I've done this. I've re-represented all this data in R. He took into account the fact that when you're looking at the star from the Earth is part of the solar system. But that's trivial compared with the size of the universe. By the way, in Hubble's time, the universe was thought to be just the local Milky Way galaxy. Can you believe it? It was after these data came in that it was realised that maybe the universe is actually a bit bigger than the Milky Way galaxy. Hell yeah. So the solar system is kind of like a little platform where he's got his telescope, and of course that moves because our sun moves through the intergalactic space at the same time. So it's called the peculiar velocity by astronomers. So Hubble corrected for the peculiar velocity. He's not fudging, but he's cranking it really hard now to try and get this thing to line up properly. It turns out the thing moved the wrong way. I put the two lines on here. These are the two lines you saw in Hubble's original plot, but I re-rendered it in R. So you might think, okay, toss it. This isn't going to work out. We can't possibly have an age of the universe is less than the age of the Earth. That doesn't make any sense. Nonetheless, Hubble published, and here's the payoff. This is data that I got from 2003, which I think is the most recent set of data that's been collected like this. Can you see the little red square there? The lower left, just down here? That's the original Hubble plot. This is out to 2003, and these horizontal lines here are, by the way, error bars, because the biggest degree of error is in measuring the distance. So it turns out Hubble kind of reached consistency, but he didn't completely have it in his hands at the time, so he had to gamble a bit. The option was you either toss the whole thing in the bin, or you publish it and hope to God that something corrects or compensates for what you've done. Hubble's basic problem was the telescopes weren't good enough to measure these quantities as accurately as we can do today. And in fact, the expansion time now has gone from 2.3 gigayears in 1929, that's Hubble's original estimate, to 13.89 gigayears now, because we know how to measure the distances much more accurately and so on. So the data was wrong, the model was correct, and he gambled on that because he had nothing else he could do. So I have this little gorilla badges that go along with the book and the past and so forth. So treating data as something divine is a sin, and Hubble recognised that. Now he took a lot of static when he published his paper originally, because people thought this is just completely crazy, doesn't line up with anything, and maybe it's the expansion of the universe, maybe it's not, who the hell knows. But as the years went by and the decades went by, it all started to line up. And Hubble was off by almost an order of magnitude in terms of this slope. But when it was all corrected, you saw the plot back here, this all works out. So he bet on the model and was correct. So don't trust the data. The data should be treated with suspicion. By the way, all data is wrong by definition, in case you didn't know that. I think I said that last year, but I'll just remind you of that. So the next thing I want to talk about is irregular time series. Because this actually came up in Monitorama last year. So the usual time series that you've been seeing in this conference are the intervals are the same because the data is being sampled. Typical performance data is all sampled, so it's like the tick of a metronome. Every tick of the metronome, whatever your sample period you choose, the data is basically snapshotted, and some things are done with it, a massage, and then that's what gets read out into VM Stat or whatever tools you're using. So performance metrics are like that, weather data is like that, but we have other time series which are irregular because there can be data that's actually missing. For example, stock markets aren't open on the weekend. Or it could be due to sampling events, probably something like what you would do for events and alarms and alerts and so forth. Or it could be subscriptions reaching a certain threshold before the actual data gets reported. Or something like measuring your own weight. So this came up in Boston Monitorama because Miner was talking about aggregating rate data, that's to say something that has the units of rate, like miles per second. He was trying to aggregate that data, to compress it. And I just pointed out to him verbally during the talk that, when you're aggregating rate data, you actually should use the harmonic mean. The only reason I said it is because I read it somewhere. I never actually used it. But I thought that's a cool thing to say because I've never been able to say that before. But to me, I said to Mike, I'm not clear about this because I've never seen this used in the context of time series. So, long story short, it cost me a month after Monitorama. I hope I'm going to get out of here cheaper than that this year. It cost me a month after Monitorama in Boston to figure out what the hell the harmonic mean meant in terms of time series. And I'm not going into that part of it today, it's too complicated. There's some slides there you can look at. I'll put these particular slides out on SlideShare or wherever after the conference. So, but anyway, that's why Monitorama is cool to me. So what does this harmonic mean? I'm just going to try to indicate to you very simply what it is in case you think this may be useful. So you're familiar with arithmetic mean, that's the usual, add up the number of numbers, add up the numbers and divide by the number of numbers. Here I'm showing it as a histogram where the intervals are the same width, the columns are the same width, there's two columns, but they have different heights. And the arithmetic mean is you take the height of the blue column, the height of the red column, and you divide by 2 because there's two columns, and you get a height of 1.5. You could also think of that as being the top area there gets chopped off and put down here so that now the two columns are the same height. In the case of the unequal interval, I have chosen same column, width 1. This column, however, has a width 3 and a height 1. If I, and an area 6 by the way, if I did the same kind of routine I just did, use the same algorithm, then operating on the heights, I would get the yellow rectangle here, which has a height of 2. And you can see that part fits in there, and the red part fits in here. They have a problem though, because the actual data goes out to a time unit of 4 width. The yellow rectangle does not. So I've got to squash it down so that I widen it out. And then everything fits, because these two blocks go down here, and that block goes in there, and it's got the correct width, 4, and the height turns out then to be 1.5 using the same kind of math for the harmonic mean. So the harmonic mean, therefore, is always less than the arithmetic mean because you've got to squash the area down. So here's an example of monitored rate data. It's actually subscriptions. I found this on the web. So they're uneven spacings, and I've just indicated there the difference between the arithmetic mean, AM there, and the harmonic mean when you calculate it for this overall time series, which I explained in the other slides. I won't come to that today. So my little message here about consistency is two things. This kind of harmonic mean, harmonic averaging, is important for rate data. Rate actually could be an acronym, which means you have to be monitoring a rate metric that you're trying to aggregate, to average out. The intervals have to be asynchronous. The threshold that you're looking for should tend to be looking for a lower threshold rather than a higher threshold, but that's not necessarily the case always. And the last one is it's going to be typically event type data in order for it to be asynchronous. So I'm actually looking for the people who have any data along these lines. Maybe you can go back and rummage around in your files. If you have such a thing, we can maybe talk about that, and maybe we'll do that in another Monitorama sometime. So I'm looking for more examples of this in the context of monitoring. So the last thing I want to talk about now is power laws. This hasn't come up in this conference. Has anybody else mentioned something about power laws? No, good. I can do that then. So power laws are important and interesting because they don't belong to the normal type of statistical distributions. And I'm going to just give you an example just to set the tone, and then I'll show you some examples that are closely related to what you do. The famous occurrence of the first power law observation was in the 1930s or so by a guy named Zipf, and this led to what we call now Zipf's law. Zipf's law is basically just counting the occurrence of words in the English language, and I've given other talks on this, so I actually pulled out a whole corpus of data and then do an analysis on this. And here you can see down here in the table, so the most commonly occurring word is the, followed by and, followed by to, followed by of, and so on in that particular corpus, which is, 4.6 million words or something like that. So the key idea is that if we plot it out, so this is not a scatter plot, but this is a plot, this is what those frequencies would look like. So that has the highest frequency on the left, and then much more exotic words have a much lower frequency to the right. So you get this kind of bow shape. But you can't tell what this function is just by looking at a plot like this. This is actually the worst way to look at this kind of thing. So here's the trick, and this is basically what I'm trying to tell you. The trick is to put it onto a plot that has logarithmic axes in both the x direction and the y direction. If the data looks something like this, it looks fairly linear on what's called a log-log plot or a double-log plot. Then I can do regression fit on that, just as Hubble did on his data, except this wasn't power law. It's the same routine. And then I can calculate the angle and so on and so forth, and I can find out the slope of that line is about 1.3. And the reason it's called the power law, I'm just showing you here, it's the logarithmic scaling on the y-axis and the x-axis. So I just take the anti-log of both sides, and I end up with something that has an equation form that looks like this: y equals 1 over x to the power of 1.13, and that 1.13 is an exponent, or a power. That's why it's called power law. And this is not an ordinary kind of distribution. This is slightly funky. The other key idea is that when power laws like this arise, they arise because of correlations that are much stronger than you would otherwise have expected. So when you see a power law, you should be thinking strong correlations. The main point I want to show you so far is that it's just a matter of putting your data on a log-log axis, even if you didn't know anything else. You just do that. If it looks more or less linear, then you could be in business with a power law. Then you'll have to understand it eventually. So persistent correlations are the key that drives these power laws, and these things crop up all over the place. I've been, year after year now, I'm finding these things in surprising places. I'm going to show you a couple of examples. In the case of Zipf's law, the correlations are coming from the grammatical rules that we use in English. This is the second example. So now this is real data. Here's a plot of that data showing the currents of the frequency of query times into a database. And like Zipf's law, we've got to modify, transform this graph a little bit so that we rank all of the data according to their frequency, and then I get something that looks like this. Still impossible to tell the functional form by eyeballing the graph in that way. Nonetheless, if I put it onto double log axes, if it all happened to be linear in the way it was for Zipf's law, I'd know I'd be looking at a power law. This particular case is a little bit more complicated, and this has stumped some database experts actually. And it's a little bit more elaborate example than I really wanted to show you, but nonetheless, this is how it worked out. So what I see here is that maybe for the first 2/3 of the plot, it is fairly linear on this log-log axis, therefore it could be power law, but something happens on the right-hand side. That power law goes away somehow or other. So long story short, I broke it into 3 pieces. And instead of doing log-log everywhere, I did log-log for the first window, that's the first chunk of the data. Second window, I did log linear, so log y-axis, linear x-axis. You see that's now linear. And log linear for the third one. So those 3 regions I can then fit. First one is power law, but the exponent happens to be 0.4632, whatever that means. And the other 2 are, because they're log linear, they are the inverse function of an exponential function. So they must be going exponentially, but they've got a minus sign, so they're decaying exponentially. So the point is, whatever the correlations are in the beginning, that are very strong apparently, leading to the power law representation, they then decay away on the right-hand side of the graph. So we've got two major things going on in 3 different places in the same data, which is pretty interesting. So if this is the case, I have to look at the power law slope, just looking at the window A, the first window. The slope is 0.46, let's say. That's about half of what it is for Zipf's law. That tells me that the correlations are even stronger than they are for Zipf's law. So that's the meaning of the slope in that particular case, like Hubble's slope. The reason that this probably has to do, the correlations are probably coming from things like dictionary lookups that the database is doing, some kind of structuring of the data. Whereas the longer term queries are more ad hoc and don't have that structure associated with them. So this is a hypothesis. I've thrown this out to several database experts and they've not really challenged it. I don't know whether it's actually true or not, but that's my current hypothesis that leads me to consistency for these data. Last example. This is an interesting one. This actually comes from Y2K period. So this is around year 2000. It happened to be in Australia. I wasn't there at the time, but a friend of mine was involved with this stuff. They were trying to get all businesses to register with what's called an ABN number for tax purposes. And every company had to have a tax number by a certain period of time. It had to be signed up by May 31st in the year 2000. This is rather like what happened with Obamacare. Not when the website went down, but when people had to sign up. And most people, the thundering herd occurred in the last couple of months. So it's a little bit like that, and you can read the details of my CMG paper if you're interested, but just to show you what it looks like. So here's the time series data, represented as a histogram in this case. And you can see the 11th hour spike because where that spike is that May 31st date, because everybody piles in at the last minute, and this actually caused the database to crash, and it's very much like a bummer can. And what's interesting here is that I can apply a power law in this particular case, even though that doesn't look like it's an obvious thing to do, and I can even predict where that spike is using a power law. So I'm not going to go into details, but just to give you the flavour, if I put that onto a log linear axis, so the time scale just remains linear, but I put a log axis on the log scale on the y-axis, then you can see that does look kind of flat. So, well, not flat, but I mean linear. So if it's linear, that means it would be exponentially growing, just like the database data I showed you a second ago. If I fit the data that way, it would look like this. So there's the function. This would tell me that it has a doubling period of about every 6 months, so people are coming in twice as many after every 6 month period. So if I then extrapolated based on that particular model, that's the exponential model, I would actually miss where that peak occurs. I wouldn't see it because the reason is because it's not accounting for the correlations that are already hidden in the data that lead to that spike. The exponential can't pick it up, but a power law can. So this is what it looks like. I'm not going through all the details, but this is where I end up without going into the details of how I did it. And here's the equation relationship, and you can see that the blue curve actually begins to peak around that point where the spike occurs, which is 61 days from the measurement period where I had the data. So I can get it to reconcile. Not easy to do, but it can be done. And this means you can actually see things in the data that you wouldn't normally be able to recognize, all based on power law. So the consistency is that log-log plots are just an easy way to test for power law distributions if they're there. So you don't have to understand anything much about the math in order to just detect whether it's there or not. You can even have mixed power law and other kinds of distributions in operation in the same data set. The database data was like that. I can even predict critical spikes in data if I've got the right kind of data set and I know how to monkey around with it. The power law is a function or a signal that there's strong correlations. That's the meaning of it. So you're then left with explaining it. By the way, the full explanation of how Zip came to see this log-log scale data in the 1930s took 40 years to figure out. It's only been recently figured out exactly how the correlations occur in the language in the right way to generate Zipf's law. So my basic point is you can see, I hope from some of these examples, what it takes to reach consistency, and that's much more important than any tools, any pictures, or any math. And the way to get there is to learn to talk to God, because she's listening. So if you're interested in anything more about this, I've got a training class coming up in May 19th, so some people came to my classes from last year, so if you're interested, there's another one running in May 19th where I talk about all this in much more detail and show you actually how to apply it. So thanks for your attention.
Questions? You mentioned something about some physicists feeling tempted to fudge the data.
Oh, yeah.
Can you talk a little bit more about maybe in our sphere of how you may have seen that happen or how people can avoid that temptation?
Fudging, you mean?
Question?
Well, I guess it's, have I seen people fudging data in your world, in operations world? Offhand, I can't think of anything. The physicists are notorious for doing this. But maybe the meaning of the stuff is a bit deeper. It's about the universe or something, or atoms or something like that. It's more important from their point of view. If I actually think of, the person that comes to my mind is actually me. I might have done some, well, I have a physicist by training, so I might have done something like that in order to be able to get the point across. You know, like there's things that don't seem to work out very well. But on the whole, if I make the assumption that that's due to some strange noise or other effects that I don't understand and nor does anybody else, and I just overlook it, I can actually make progress. And that triple database data that I was showing you, where I do the power law plus 2 exponentials, is pretty zany. I don't know anybody else has ever done that. But every other database analyst that had looked at that data was trying to fit things like Poisson and Gaussian and God knows what, getting absolutely nowhere. And I played around with power laws a lot, so I don't know what to do, but then even that didn't work. It wasn't pure power law, it's power laws plus some other things. And that looked very odd to me in the beginning, but I thought, well, what the hell? I mean, maybe that's actually really there. And because I remind myself that it's to do with correlations, I can argue that the correlations are strong in window A and weaker in window B and C. I have no idea why. I don't know anything about databases and I don't wish to know anything about databases. But I can then take that interpretation, my point of consistency, back to the database experts and say, well, what do you think of this? And they might say that's trash, in which case I have to go back to the drawing board. But nobody has so far. I tend to work at that a lot so that that doesn't happen. So it's not about that's exactly fudging, but it wouldn't be beyond me. I might try to fudge something if I thought it would make a lot of progress and provide an insight that nobody else is going to get anyway, so what the hell? I mean, it's a bit like Hubble. You've got to have the conviction of what you're doing. It's, it's not the tools, it's not the pretty pictures, it's what the hell does this really mean and do I believe it? I'll give you a little side story now I think about it. My first undergraduate physics supervisor, I had to write a minor thesis in 4th year, and he's Hungarian. Hungarians are all a little bit strange, by the way. And, but he was a great guy, and we worked very well together. And I was a student. Now, students know nothing, but you think you know everything. And when I would go to see him on a regular basis to show him, what great things I've been doing and what things I read, he would just be sort of casually standing there and he'd say, that's very interesting, say, but how do we convince ourselves that's true? And I'm thinking, what the hell are you talking about? I spent the last week reading this, it's in a journal or it's in a textbook. What do you mean? Is it true? I wasn't saying this to him, I'm just thinking, what do you mean? How do we convince ourselves this is true? And that sounded to me so stupid, I mean, what more can I do than read about it? And then I gradually began to realize this is actually the most important statement or question that any scientist or engineer can ask themselves. How do you convince yourself that whatever you're looking at is the correct thing as opposed to something different? That takes a lot of hard work. And so if I'd try to get a conviction about something, basically. If I have that conviction, I'll become extremely stubborn about it, but until somebody can convince me that I don't have it right yet. But at least I have a position, and then other people can reference my position and say, oh, well, that doesn't sound right, but we can't come up with anything better. And that's not a bad position to be in either, by the way. By the way, that's Einstein's technique. Einstein does things, well, he got carried away with the math eventually, but in his very early papers, the Annus Mirabilis, 1905, he did 5 papers, all of which could have gotten in the Nobel Prizes in any case. If you read those are readable by almost anybody, because it's relatively low-key physics, but it's what he does with it that's amazing. And his technique is to basically start out with some broad statements that everybody can buy into, and then it's like he moves you down a corridor and he's closing doors behind you as you move down. It's like, yeah, okay, I can buy that, I can buy that, I can buy that. And then at the end, he will come up with this amazing conclusion, which you think, well, okay, that's reasonable based on everything you said beforehand, but on the other hand, it's completely outrageous because who thought that before? We didn't know that before. And his point is, he doesn't say it this way, but you get the feeling that what he's doing, he's now painted you completely into a corner, and he's saying, not only have I explained it, I've explained it in the simplest terms that I could come up with. If you think you can do better, you come up with something simpler. And because he's worked so hard, he knows that's not going to happen. And therefore, he could launch these papers. I mean, one of the papers in 1905 proposed that light was made of photons, particles. We all believe this today because you've heard it so many times. In 1905, there was an outrageous statement. He got a lot of flack for that. And even when he got the Nobel Prize for it, Max Planck said, we're giving it to this guy, we're letting him into the academy and so on. He goes over the top a lot. But on the other hand, it's not bad work, it's fairly reasonable work, so he should be doing it. But he had a conviction of what he was doing because the other thing I should say is that he and other physicists typically use the simplest ideas, not the most complicated ideas. Okay, if you don't need the fancy math, then toss it away because it's just going to confuse you and everybody else. So it's as simple as possible, but no simpler, of course. I don't know if that answers the question. I had fun talking about physics. I think there's one at the back there.
Yeah. Hubble's estimate was wrong because the fidelity of his measurements were incorrect. The light were low. You can bad numbers because his telescopes weren't accurate. It seems like in our sampling, our measurements are perfect for only 50 months. To a very high precision, like what the amount of time that it takes for something to happen. We're very, very accurate. So it seems like our challenge is teasing the signal to signal-to-noise ratio problems in our experiments. So, or our measurements. So, does that change the way that we need to? Does that change the way we need to check ourselves? Like Hubble could say, this comes to an absurd conclusion, but my data is probably inaccurate, so my model is probably correct. We don't really get to say that. Does that change the way that we need to?
Actually, I think you do. I mean, I've certainly gone through circumstances where I don't have to repeat the question. I don't know what it was. What was the question in 5 words? Oh, so do we need to do something different from Hubble in terms of how we use the data and draw conclusions from it? Is that a statement? Something? I mean, I really don't think so. I mean, first of all, as I said before, all measurements are wrong. So the only question is, how much of the wrongness can you tolerate, and how much is it going to creep into whatever explanation you have for whatever's going on? So you're right, though. I mean, you don't usually have the Hubble problem in that sense. That's showing a better accuracy than that. But that doesn't necessarily mean that all the data's hunky-dory and that you should necessarily trust it. I certainly wouldn't. And, you know, I mean, many cases where the data is measured quite accurately, but it's completely wrong. By the way, this is not exactly the answer to your question, but I have another very good example from physics. A couple of years ago, some physicists in Italy were measuring neutrinos coming from the Large Hadron Collider in Switzerland, and they came up with a remarkable result. The data was indicating that some of these neutrinos were traveling faster than light, called superluminal. If those data were correct, then Einstein just took a big hit. And by the way, the accuracy of that data was 6 sigma. 6 sigma accuracy. Turned out the whole thing, by the way, they diddled over whether to publish this result. After some months of dithering around, the team decided to publish the paper. Within a month it was retracted. And the reason is because although the data had precision of 6 sigma, the thing that was causing the data to show superluminal neutrinos was a 50-cent connector. It was not attached correctly to the instrument that was supposed to be doing the measurement. The guy in the team who put the connector on forgot to lock it. When you locked it, you know, it's a fibre cable. When you lock the fibre cable, boom, all the superluminal stuff goes away. But the data was accurate to 6 sigma. By the way, the test for particles at the Large Hadron Collider, like the Higgs boson that was discovered apparently, it's only 5 sigma as a criteria for that. These superluminal neutrinos were 6 sigma accurate. So high precision on garbage doesn't, you know, improve the situation. So yeah, I think I have seen situations like that in the context in which you're talking about. So I'm extremely skeptical about data. Forget the precision. You know, do I really believe this? And one of the only ways to do that is to try to find a framework in which to put that data and see does it fit, like Hubble had the linear idea that it's linear. By the way, that's completely philosophical bias. He wanted to believe that. He wanted to believe that. So there's many cases in physics and science, like Mendel's peas, for example, the thing that led to the genetics. You can't do an experiment like Mendel did in the back of the Abbey and come up with a ratio 9 to 3 to 3 to 1, because you don't get integers like that. If you look at the data, it's some screwy numbers. So how the hell did he get the idea of the gene? Because he had it in his mind. It's a philosophical bias. Those numbers are just a very, very poor representation of my 9 to 3 to 3 to 1, which I fully believe is there, if only we could get the data to line up the right way. And that was correct. That was correct. So a lot of progress sometimes comes from these huge leaps of faith or philosophical conviction or whatever you want to call them, because sometimes they're wrong. Hubble was afraid of that, but he decided to go with this conviction, much the same way as Gregor Mendel and his peas. And he got lucky. I don't think, you know, at the 1921 it wasn't so clear what was what, whether the universe was expanding. You couldn't improve the telescopes at the time. The other big problem actually is not the telescopes, it's how do you think about it, you're looking at a star radially, how do you tell how far away it is? Very, very difficult thing. Astronomers had a procedure for that. The procedure that was available at Hubble, which was the newest idea at the time, called Cepheid variables, turned out to be not accurate enough. Today we use type 1 supernova, which is much more accurate because we know the spectrum. And you still saw that on the graph, the biggest error bar was in the horizontal direction, the distance direction, not the velocity. The velocity you can measure by the redshift very, very accurately with spectrometer. The radial distance is the trickiest part, and that's really what tripped Hubble up, but it's very understandable. Nonetheless, you could have thrown it in the waste bin and just said, okay, this doesn't line up. I don't want to embarrass myself by pretending it's a linear relationship to do with expansion when I can't justify it from the data. Now, he didn't do that, he did exactly the opposite because he had a philosophical conviction that this is probably right, it's all messy, but it's probably right. But that's a gamble. Usually you guys don't have to face that kind of a gamble, I don't think.
Actually, I want to make a point here. Most utilization measurements in computing are very inaccurate.
Yep.
You can measure time well, but it's very, very hard to measure utilization. And most of the time you're not actually measuring what you think you're measuring.
Right, and then there's also
Four different ways of measuring utilization, they won't line up.
Yeah. So yeah, it's certainly true. I mean, I see inaccuracies all over the place, but yeah, not to the degree that the Hubble problem, but certainly there I would be very skeptical about that. Until I can find a framework where I put it into the framework and see that it starts to match up in some consistent way, then I might start to accept it. Somebody else has a question?
Yeah, I mean, you talked about consistency, and I've been struggling with the eventual consistency problem. You know, Amazon, Stack, they all are not consistent services.
Right.
They are eventually consistent services.
Yep.
And as such, you have to deal with all the problems of an eventually consistent system, including in your monitoring.
It's a different kind of consistency, but I know what you mean.
Okay.
Yeah. So yes, I mean, any framework that was looking at data coming from such an environment would have to take that kind of, the other kind of consistency into account. Yeah, sure. I have a whole thing about scalability, quantifying scalability, where I deal with that problem actually, but I don't have the guts to give that talk here yet. I think it's too much of a gap, but I think we'll close it down eventually. Yeah, in the back.
So in the last example where you used power law,
Yes.
you were able to figure out it was power law after the fact. Now let's say the event were to happen again. Where would you be? What's the guarantee that the same kind of power law will play out again?
Yes, you need, you're right, yes, okay, I don't talk about that here, but so there is a way of algorithmically looking at data to do what would be the equivalent of a power law detector in that sense. So you can algorithmically construct such a thing. I don't have time to do all that today, but it can be done. I talk about it in my classes, but it can be done. You know, I'm not saying it's always correct, or but it's another tool that you can use to do things like that. When you've got new data coming in that you don't know whether it's there or not. So yes, you can construct a kind of power law detector. The background for knowing how to do this is a little bit complicated, so that's why I didn't do that today. But it can be done.
Would that be based on assumptions about like human behavior? So you're assuming that people approaching a deadline would behave in a certain way. Is that factor to it?
It's interesting, just remind me of something. So, something with human behaviour? Not necessarily. No. That I would think of as being an explanation after the fact. If I can convince myself that power law characteristic is there, then I might refer to human behaviour in order to explain why it's there. It's a different thing. But you just reminded me of something. Last year I was working with a client, actually a big insurance company in California, and there was, had sampled data. Insurance companies do this massive parallel processing stuff to process claims and so forth. So the parallel processing system was being monitored in the usual way, and we were using those data to build queuing models and predict bottlenecks and all that good stuff. But then along the way came this separate episode where we had data, not from the machine itself, but it didn't conform to the usual types of rules that you would like to have available to be able to use things like queuing models, and so it was completely different. And when this came up, I couldn't really get anybody to explain it very clearly what the hell it was they were talking about. So then I got the idea, well, do you have an example of some of this data that you're talking about? And they did. So they sent me the data, and I looked at it, and for one reason or another, I had the idea that, you know, this might be parallel. So what do? You put it on log-log axis, right? Dead simple. And boom, there's the line. And now the issue was, if it's power law, it certainly looks power law, how do I explain this? And the explanation, it turned out, because I was clueless, you know, I usually didn't know what the hell's going on. I just do some stuff with data and then let other people fill in the gaps. So it turned out that this had to do with the fact that every now and again, the parallel processing system sent for certain claims will stop. It's in the design of the application. It will stop because it needs to have a certain verification or a number or some other input that has to come from a human. There's no way to do it in an automated fashion because things are changing too fast and so forth. So a human has to intervene into the processing. And it turned out that the delays were power law delays. But of course, it's a human, and very quickly you figure out what's happening is that if the human happens to be at the console where they enter all of these additional details, at the time that the event occurs where the parallel processing system makes the request for that information, then the time will be relatively short. If, on the other hand, they've gone to the bathroom, who knows how long that's going to take, or they might have gone to lunch. So the times will then be very long. But they're correlated with this human behavior. What was amazing was nobody thought it was at all possible to be able to model this stuff in that sense. And it turned out not only could you model it, it's a power law. In that sense, it hardly comes any simpler because it's just a log-log transform. And we even knew why when we looked back on it. So the human behavior stuff did come in there and it all kind of fit together. So it was actually really quite intriguing.
I'll take one last question in the back.
What made you choose the log-log transformation as the best example? Are there others that are nearly as applicable or nearly as useful to us?
You mean why did I?
That particular transform, that particular law, it proves, here. In other words, are there others that you use that we might bring there as well?
Oh yeah.
That proves
Well,
the utility of this one.
yeah, well, there's lots, but the reason I decided to talk about this one today is because it's so simple to do the log transform to see if the data tends to line up in a linear fashion on the log axis. It's relatively easy to do. Explaining it and understanding the fitting and everything, that's more tricky, but it can be done, obviously. But I'm just showing it to you as an alternative, which is very easy to do, as opposed to, say, some of the transform, which is more complicated to do and more difficult to explain. It's an easy thing to do that you wouldn't normally think about. That's the reason I brought it up today. Does that make sense?
Yeah, absolutely.
Okay, so I've got lots of transforms in my back pocket, but this is a simple one, and not some people generally don't understand this stuff very well. And it's easy to do, and it's easy to convince yourself that the power law might be there. And don't worry too much about explaining it. If you get into trouble, send me an email. I'll try to help you. But you wouldn't normally think of trying to use such a simple detector in that sense, after the fact, of course. But it's a very easy thing to set it up and just put it in a plot and whatever tools you use, and boom, you're done. And you won't get that from normal statistics. It's kind of out of the normal statistics zone, because the power law has very peculiar properties in terms of what a statistician normally thinks about. But that's okay, stats not math anyway, so that really don't want to do it. Well, thank you for your attention and questions. It was great.